In this problem, we are tasked to determine the maximum torque in Newton meters that can be applied to a hollow circular steel shaft of 100 millimeters outside diameter and an 80 millimeters inside diameter without exceeding a shearing stress of 60 megapascals or a twist of 0.5 degrees per meter. Use a shear modulus of 83 gigapascals. And to solve this problem, we consider two cases, one in which the shear stress must not exceed 60 megapascals and the angle of twist for the shaft must not exceed 0.5 degrees per meter. So first, let's consider the case where the shearing stress must not exceed 60 megapascals. So based on shear, we have the formula for torsional shearing stress that is equal to the torque applied times the outer radius if you want to solve for the maximum shear divided by the polar moment of inertia. We have the shear stress equal to 60 megapascals or Newton per millimeter squared equal to the torque T, which we need to solve, multiplied by the outer radius that is equal to 100 divided by 2, that is 50 millimeters, divided by the polar moment of inertia. And since this is a hollow shape, we subtract the polar moment of inertia of the outer figure or the outer circle, that is pi times 100 raised to the 4th power divided by 32, minus the polar moment of inertia for the inner circle, that is pi 80 millimeters raised to the 4th power over 32. And we can solve for torque. You have 60 equal to the torque T times 50 divided by pi times 100 raised to the 4th power over 32 minus pi times 80 raised to the 4th power over 32. Shift solve, we get torque equal to, that is equal to 6,955,486.135 Newton millimeters, and this is based on shear. And now let's consider the case where the angle of twist for the shaft must not exceed 0.5 degree per meter. And the formula for the angle of twist that is equal to torque T times the length divided by the polar moment of inertia multiplied by the shear modulus. And we have the angle theta, or the angle of twist, that is equal to 0.5 degrees. Converting this into radian, this is pi times pi divided by 180 degrees. This is equal to the torque applied times the length of 1 meter, because we're considering 1 meter for every 0.5 degree of rotation. Or in millimeters, this is 1000 millimeters. Divided by the polar moment of inertia, which is equal to pi times the outer diameter, 100 raised to the 4th power over 32, minus the polar moment of inertia for the inner circle, that is pi 80 millimeters raised to the 4th power over 32. And then we multiply this by the shear modulus equal to 83 gigapascals or 83,000 megapascals, which is also equal to Newton per millimeter squared. Now we can solve for the value for torque based on the angle of twist. We have 0.5 times pi divided by 180 equal to torque T applied times 1 meter or 1000 millimeters divided by the polar moment of inertia. We have pi 100 raised to the 4th power over 32 minus pi times 80 raised to the 4th power over 32 multiplied by 83,000. Shift solving, we get T equal to 4,198,282.792 Newton millimeters. And this is based on the angle of twist. Now, based from these two values, the maximum torque for the shaft to not exceed the shearing stress of 60 megapascals or an angle of twist of 0.5 degree per meter is the one that has the smallest value, which is this one, so as to not exceed the shear stress of 60 megapascals or the angle of twist of 0.5 degree per meter. And since the problem asks us to find the torque in Newton meter, we convert this, or we multiply this by a conversion factor of 1 meter per 1000 millimeters. So we can get our answer in terms of Newton meter. Here, dividing by 1000, we get 4198.28 Newton meter. And that is our final answer.